All right, everybody. Welcome back, I guess. Uh, the discussion before recording has been good and positive, too. So a couple things that need to be talked about in announcements. One of them, let me just change that. There we go. Is that I did send Hayden McNeil a trouble report with regards to question 9 on the short answer for this experiment that you're doing, and it took them 2 days to get back to me saying, thank you for that advisement, we'll look into it. So their idea of rapid response appears to be a week or two. My idea of rapid response is like a day or two or less, depending on the seriousness. That said, one student believes quite strongly, actually, that the figure that is missing from the short answer question is actually a figure in the pre-lab. And if that's the case, I can go in there and grab the figure and put it in. They're going to send me an email. I'll look at it this afternoon and see if, and if that's, like I said, if that's the case, I will be able to fix it and go from there. That said, where were we going to go with that? I should bring back the floating head. Yes. Halloween, this fall, you take class with me, we'll bring back the floating head, but we're going to be face-to-face this fall, so I don't want to have my head detached from my body for real. That would be not good. So, that said, with regards to the experiment that you're working on, there is going to be one additional quiz. The reason why I put this experiment, which is the solubility of salts, here is because it links to thermodynamics, the unit we're going to be starting today. Now, the link is not in the standard questions that are being asked of you, but doing a very simple analysis, literally plotting a graph, you will be able to calculate the enthalpy and the entropy of the dissolution process. So I'm working on, I actually asked a couple of students to send me their data, and they did, and it looks like it's going to work just fine. So what I'm going to do is I've created another quiz that's going to be added on that's going to apply thermodynamics to your data analysis, and that's also why I've given you an additional week to submit this quiz, is because we're going to be starting the thermodynamics unit now, and we'll cover that material around the time that you need to submit it. So just saying that that's good. Additional quiz, class, yes. That's about it. Does anyone have any questions or comments with regards to the lab component? You like the floating head. All right. Doesn't look like there are any serious questions, so let's go back to this, and let's start looking at this unit. Now, we are going to be looking at thermodynamics. In Chem 100, you had thermochemistry taught to you, or taught to you. That is enthalpy. We're going to build on that material basically in this chapter on thermodynamics. So to remind you, we actually saw this page when we looked at kinetics at the beginning of the course. Thermodynamics and kinetics ultimately provide complementary information on chemical systems. When we did kinetics, I was focusing on the kinetic component. Here I'm focusing on the thermodynamics component. Thermodynamics investigates the direction and extent of a reaction. And as you can see here, thermodynamics, is the energy difference between the reactants and products. Kinetics, of course, is the energy from the reactants to the barrier. So thermodynamics identifies the most stable state. It identifies the equilibrium position. Kinetics tells us how long it's going to take to get to the most stable state, or if it's at all possible. On Blackboard, I have put up the problem set for the thermochemistry unit. It is not for marks. It is just there. You actually already also have the answers. It is just to remind you of calculations involving enthalpy. the problem set that is, of course, relevant to this thermodynamics unit is also up there, and we'll be covering the material for that over the next week or two. We'll get to that in just a second. What I want to do now, because we didn't do any demos for the we didn't do any demos in the intermolecular forces module. I do have a few demos that are thermochemistry related, but are interesting and fun and a little different. And I'm just going to be a little bit cheat because I need a broader camera than what I have. So we're just going to do that. And we're going to move this closer. So just give me a second. So, when I talk about thermochemistry, I often relate it to the real world. That's kind of a really good instructional strategy to see how this applies to the real world. And of course, we don't unfortunately have any, or I haven't been downtown enough to see, but if you go to a bigger center where they have parking garages that go up, or underground parking areas for buildings, there will always be a sign that says no propane powered vehicles in the underground parking area. No propane powered vehicles in the underground parking area. When we discussed gases in Chem 100, what we learned is that we can calculate the density of a gas. And the density of propane vapor is heavier than that of air, nitrogen and oxygen. So if you have, okay, let's back up. If you have a leak of a gasoline tank, okay, there's a puddle underneath the vehicle, and someone will point out and go, hey, there's something leaking from that vehicle, and you figure out if it's the radiator, if it's oil, or if it's gasoline. It's localized to a given vehicle. However, propane, being a gas, leaks, and it just distributes itself everywhere. And because it's heavier than air, it settles to the bottom. Hence the sign, no propane-powered vehicles. What we have here is an enclosed container. Underground parking area is a reasonable enclosed container. And now imagine you're with someone who smokes. You don't smoke, of course, but you're with someone who's smoking. And you're walking down the ramp into the underground parking area. Quite hot, very hot actually. Now what I want you to think about is this occurring all around you. It's occurring in the hair that you used to have, okay? You've also breathed this in. So not only is it occurring all around you, it's occurring in your lungs. It was an expansion process. So it is expanding, breaking the alveoli, and coming out your throat, your nose, whatever, where it happens to be, or rupturing your lung into your chest cavity. Something like that can and has killed people. And why there's a sign, no propane-powered vehicles in the underground parking area. I'm back. Not quite a floating head, but, you know, bit of a quick change artist somehow, somewhere. That's one example of that. Anyone put anything in the chat to discuss this? I blinked when it happened. Yeah, it's okay. The reaction was golden. You guys are awesome. Here's an example of it happening not with propane, but with natural gas. I was actually teaching this day, and because this happened in New York at around 5:30 in the morning, it was literally front page news, and I took it into class as it's really rare that you get current events in chemistry. This was current events, and I was actually, well, look at the time. It's March 12th. Today's March 19th. At the time, I was actually teaching this material, so it actually fit in just beautifully. Excuse me. So this on the left-hand side is a Google Street View of shops on the main floor and apartments up above. Not a problem at all. And what had happened is that someone got up at around 5:20, 5:30 in the morning and flicked on a light switch and turned the entire building into kindling, as you can see on the right-hand side. Now, this picture was taken from across the street where all the windows had been blown out because of the detonation. What is, whoops, oh, sorry. Does that help? My apologies. My apologies completely. So yes, on the left-hand side, Google Street View. On the right-hand side, what happened at around 5:20, 5:30 in the morning. Person flips on his light switch and turns the building into kindling. Light switches are really a hazard. Yes, Mark, they are. Okay. We'll move on from that. What had happened, and this is from reading the news article, it's very common for people to smell gas in buildings, but because the plumbing is upwards of 100 years old in some buildings, it's hard to find the leaks. And when they find one leak, there might be a dozen more that happen. And so just by someone shifting an appliance or a little bit of an earthquake or something like that would have caused the leak in this building, and it just filled up overnight. Now natural gas rises, fills up the area, and 5:20 in the morning, someone flipped the light switch and boom. I'm glad the chat isn't recorded for my purposes. Sheesh. You guys are silly. That's not from a light switch. That's from a light switch being the detonator to a bomb the size of the building. So yeah, not good. It happens. In Edmonton, there was an example of someone's house where they were doing work. The question as to whether it was intentional or not is still up in the air, but what ended up happening, there was a leak of either propane or acetylene, don't know, and it ended up detonating not only the house, but 3 houses around it got damaged or demolished because of the one detonation in this one home. Whether it was intentional or it was an accident is uncertain. Whether it was acetylene or it was just natural gas is uncertain as well. But it was a very bad thing. Several people died, not only in that one house, but in adjoining houses as well. People cooking in the chat, someone talked about people cooking meth in the garage, and yep, that happens. Now this is the fumes aren't natural gas, but they need to use, don't ask me how I know this, like seriously, don't ask me how I know this. Gasoline is commonly used to extract the crystal meth and to purification process, and so the gasoline or naphtha, either of them work just fine. Vapors will be all through the air, and the people that are doing this, yeah, they smoke. Boom. Not good. It happened in St. Albert, Alberta as well. So we are going to be looking through chapter 13. I think chapter 6 is thermochemistry. We're doing chapter 13 on thermodynamics. These are the units we're going to be covering. I don't teach separately Boltzmann's and Clausius's view per se. I just put it all together in one stream of consciousness, and so we combine them all together because ultimately that's what we use today. We use the combined thought processes of these two separate perspectives on entropy. Section 1318 has a lot of math in it. We're going to look at it strictly from a conceptual view, not from a mathematical perspective. So to start, we need to talk about spontaneity. And in terms of spontaneity, we have the idea of a spontaneous process is something that occurs if left to itself. So without outside influence, without outside intervention, If I were to put a piece of iron outside, it's going to rust. Something really hot is going to cool down to the ambient temperature. Water is going to flow downhill, plants are going to grow. Those processes are spontaneous in the environment in which they are occurring. I don't have that video, but yeah, we don't have that video. On the other hand, a non-spontaneous process will not occur unless there is some sort of external energy input. That sentence itself is not exactly true. An non-spontaneous process never occurs. What that external energy does is it changes the condition so the process becomes spontaneous under the new conditions. So a non-spontaneous process will never occur. The putting energy or changing the conditions to make it occur actually changes the conditions, and so the process becomes spontaneous under those new conditions. I'm just going to give you a few seconds since you had a bit to write down there. The key phrase, the external energy changes the condition, so the process becomes spontaneous under the new conditions. Here's a couple of examples. I mentioned iron. If I were to put a piece of iron right now outside in air, or water contains oxygen as well, iron in an oxygen-rich environment at ambient temperature will spontaneously rust. Kinetics says it's going to take a while, a couple thousand years, but it will rust away. However, the reverse reaction doesn't occur under ambient conditions, but it does occur when you remove the oxygen and you put it at elevated temperature in a carbon-rich environment. So iron oxide, high in carbon, at 1800 Kelvin, will react to produce liquid iron and carbon dioxide. The temperature is to address the kinetic problem. The kinetic barrier is high, so increasing the temperature makes this reaction occur on a reasonable timescale. Now, historically, that carbon was sourced from coal. And if you're following the green revolution that literally started happening about 3 months ago, because I came from Alberta, and Alberta is stupidly talking about mining the Rockies for coal, yet coal is a surplus and there's not enough markets out there. It's just weird. Anyway, you can also do this reaction not with coal, but with hydrogen. And there are hydrogen smelting plants being built around the world to not use coal, not produce carbon dioxide. With hydrogen, you actually produce as a product water vapor and liquid iron. So there's another way of doing it that doesn't require coal, and it is environmentally greener. Let's look at the hydrogen-oxygen reaction to produce water vapor. So under normal conditions, hydrogen and oxygen are going to actually react explosively to produce water vapor. And in a controlled environment, this can be used as a rocket fuel. It is used as a rocket fuel because it's environmentally safe as well. In order to take water and split it to give you hydrogen and oxygen, you need to change the conditions, and in this case, it's by putting electrical energy in. Anything greater than about 1.22 volts will split water vapor into hydrogen and oxygen. That can then be stored, used for hydrogen economy, used medical oxygen. All of these things are possible there. Just out of curiosity, Taylor, did you mean to misspell that, or was that intentional? Can't type. Okay, it's funny because I've heard, yeah, that's something. Never mind, I'll just move on. Let's look at entropy. We need, the entire reason for this chapter is to figure out how we can tell if a process is going to be spontaneous or not. So we need an indicator for spontaneity, where if it's in one state, it's spontaneous. If in another state, it's non-spontaneous. We have enthalpy already, and it would be nice that if a reaction was exothermic, it was spontaneous. If it was endothermic, it wouldn't be spontaneous, but that's not the case. Endothermic reactions occur, exothermic reactions occur. So we can't use enthalpy as an indicator for spontaneity. We're going to use entropy, given the symbol S, I don't know why, and we're going to see by the end of that we're going to introduce entropy, and it's going to help us get to a spontaneity indicator. What is entropy? It is the measure of dispersal of energy, how the energy is distributed within the bulk, within the sample. This is Boltzmann's contribution to entropy, one of the first people to study and try to get a grasp of this process. And what he derived is a fundamental formula for calculating entropy, and that is entropy is equal to Boltzmann's constant times the natural log of the number of ways of distributing the energy amongst the available energy levels. So we're going to look at that in more detail in just a few seconds. Okay, that works. So Boltzmann's equation, S is equal to KB ln W, is fundamental to determining the entropy of a system. Now, normally in a regular class, this would be where I would ask the audience for audience participation, and I would need to borrow some coins from students because I don't have anything in my pocket. Quarters, loonies, toonies, I just don't have that. So unfortunately, we don't have the ability to do that. However, if you do want to e-transfer me a quarter or a loonie or toonie, that would be okay too. Forget I said that. Forget I said that. Anyway, we're going to have to pretend about that. We're going to pretend. What's your email? There you go. Thanks a lot. So my email is actually quite common. What is the probability? Okay. Now let's talk about it in the context of flipping a coin. So imagine I had a quarter. It would also that would also showcase how bad I am at physical tasks. So if I'm flipping a coin, the probability of that coin coming up heads is 50%, okay? 50% heads, 50% tails. If I had another coin, the probability that it would come up heads is also 50%. Now, if I take the two together and I flip them, what is the probability that they both are heads? Anyone? .25. How do you get 0.25 from flipping two coins? What do you need to do with the individual probabilities to get the overall probability of the combined event? You multiply them. Excellent. Right. 0.5 times 0.5 is 0.25. So we apply that to all systems. If we have completely independent events and we want to see how the combined system operates, the probability of a combined system, we simply multiply the independent probabilities. Exactly. So, sorry, my error. When we do 3 coins, now we have 3 coins going through, and in order to get all 3 heads, it's 0.5 times 0.5 times 0.5, or 0.125. Those individual outcomes are called microstates. Both heads is a microstate. Both tails is a microstate. One head, one tail, one head is a microstate. So there's number of ways in which we can get all those possible microstates. Excuse me. And we can see for 2 and then 3 and then 4 coins that the number on the edge, the outer limits, continues to go down. 0.25 to 0.125 to 0.063. And the difference between the outside edge and the center continues to increase. Here the center is double, here it's triple, and here the center probability is 6 times the outside edge. There's a lot more ways of distributing 4 coins such that you get 2 heads, 2 tails than there is of getting all heads or all tails. Where do we apply this? We can apply this in chemistry here. If I have 2 flasks joined by a valve such that one flask is filled and the other flask is empty, what happens when the valve is opened? Anyone? What happens when the valve is opened? Not diffusion, because diffusion would be faster, but you do get an equilibrium. They mix. There's nothing in one flask, there's something in the something, and you basically get the gas distributing throughout the entire volume. My question for you is, if I were to put pressure gauges on each of those 2 flasks, would I randomly be able to detect a difference in pressure, right? We saw, let's back up here, that we have some probability of there being 4 and 6 and 4 down here. So there's some probability in this region such that there is a little bit of a difference. Are we going to see that difference when we have a lot of gas molecules going through a flask? Not 1, not 2, not 5, but a reasonable sized flask has 10 to the 20, 10 to the something gas molecules in it. Benjamin says no, and we're going to figure out if he's right using this exact same process that we are applying right now. Not any observable quantifiable amounts? Well, let's prove that. So envision the flask now has 2 gas molecules. We just did it with coins, but with 2 gas molecules, you get the same distributions. You get both in one side, both in the other side, or 1 in each. We can do it with 3. We can do it with 10 gas molecules. And this is what the distribution looks like when we have more and more gas molecules. You can see that it is basically 0 out to the extreme, and the distribution keeps getting narrower and narrower and narrower as we have more and more gas molecules. It gets to the point where with 10,000 gas molecules, it really has only a small width around 50-50 distribution. You're not going to see 25-75 when you have 10,000 gas molecules. How about when you have 10 to the 23, which is 1 mole of gas molecules? Okay, 10 to the 23 looks very much taking that down to an absolute thin line. It is exactly at 0.5, and it doesn't deviate at all. For those of you out there who have taken math, maybe taken calculus or enjoyed it, there is a term for this type of distribution, which is 0, 0, 0, 0, 0, 0, 0, infinite. Anyone happen to know what that distribution is called? It's not called a limit, no, 0, 0, 0, 0, 0. It's a discontinuous function that goes basically 0, and at one point it goes up to infinity and comes right back down. It's not an asymptote, no. It is called a delta function. So it's called a delta function, and you'll learn it if you continue taking calculus classes. Oh, you also learn it if you are in engineering and start doing electronics, because it becomes a issue somewhere. I don't, off the top of my head, I can't remember where. Delta functions are bad. They're effectively spikes that cause problems for electronics. This is, we can apply that to this process and get, the application of mathematics in chemistry. You basically don't see any width on that distribution. How about, we're now going to look at the idea of microstates that helps us understand how we distribute the energy amongst the available particles. The idea of microstates is we're going to start off with fixed energy and fixed number of particles, and not in this class, but if you continue on in science into a field, physical chemistry, you will learn the concept of statistical mechanics that's going to take it from 3 or 4 or 5 particles up to millions and billions of particles to the bulk states of matter. So given 2 particles with an available energy of 4, how many ways can we distribute this energy amongst the particles? Well, obviously we could have 1 particle with 0 energy and 1 particle with 4 units of energy, or it could be the other way around. The first particle could have 4 units of energy and the second particle could have 0. We could do the exact same thing with 1 and 3. 1 and 3, or 3, oops, my bad, and 1, like that. So there's 2 ways of doing 0 and 4, 2 ways of doing 1 and 3, and the last is to have them both here. Oop, that didn't work either. Right there. Both at 2 and 2. So there are 5 ways of distributing 4 units of energy amongst 2 particles when the energy available units spacing is integer. That's actually on this next page. W equals 5 as presented here. The rest of these graphs do the same thing for a variety of different number of particles and number of available energy. In this first one, going over to B, we now have 6 units of energy still with 2 particles. And here, with more energy available, W now equals 7. We have 1 and 6 times 2, sorry, 0 and 6 times 2, 1 and 5, 2 and 4, and 2 at units of 3. That's cool. 7 different ways of distributing it. So when we put energy in, we increase the number of ways of distributing the particle. And if you go back to Boltzmann's equation, S is equal to KB ln W, we increase the entropy when we increase the energy. This one still has 2 particles and 4 units of energy, but there's more energy levels. There's now integer and half integer spacing. So we can have 0 and 4, 0.5 and 3.5, yeah, 1 and 3, 1.5 and 2.5. So there's more ways in which we can distribute the available energy amongst the particles because there's more energy levels available. And finally, if we have 3 particles with 4 units of energy, we have, again, more ways of distributing the energy in the sense that we have 0, 0, 4, 3 ways of doing that. Any one of these can go up. 0, 1, and 3, when the distribution here is 6 ways in which we can distribute these 3 particles with these 3 energy levels. And I'll leave that as an exercise for you to confirm permutations, combinations in math, or just work it out by putting, if we label the particles A, B, and C, you can figure out that there's only 6 ways that we can distribute the energy amongst those 3 particles. 0 and 2, and then 1, 1, and 2, and distribution. So basically, increasing the number of particles increases the number of ways, increases the entropy. With 3 particles, that last one, there's something interesting that actually happens. If we add up the number of particles that exist at energy level 4, 3, 2, 1, and 0, we find that we have this profile. And it's basically saying that there is more, I can't draw a straight line, but you get the idea, more molecules residing down here at lower energy than at higher energy. Does anyone remember where you've seen that before? Where there is more molecules with low energy and fewer molecules with higher energy. Flip the page in your notes. It was in Chem 100, and in Chem 100 you were looking at the concept of gases. We actually saw it in kinetics here as well, but I believe it would have been introduced to you when you were talking about gases and distributions, where you'd have what's called the Boltzmann distribution. I'll get back to that in just a second. The Boltzmann distribution, Maxwell-Boltzmann distribution, has a lot of particles with low energy, and then it tails off at higher energies. This, when you actually take these distributions and you, when you take these distributions and you expand it using statistical mechanics to real atoms and large numbers of them, you get the Maxwell-Boltzmann distribution as presented here. So the note at the bottom is that, yeah, real systems have more energy levels, more energy, and more particles. And so StatMech allows us to actually derive the Maxwell-Boltzmann distribution. So for example, we want to determine the number of microstates with 3 particles and 3 units of energy, and energy levels are spaced at integer increments. And then we want to determine the entropy of the systems, or at least one of those systems. So I'm just going to go back up just a tiny bit to this one right here. And here is my energy level diagram, except now I'm working with 3 particles and 3 units of energy. So the obvious one is 0 and 3. And there will be 2 ways of doing that. One of these can go down, different one down or up. Another option would be to have 1 unit at 1 and another unit at 2. Oh, there's 3 particles. My apologies. So this is 0, 0, 0, 0, 3, and that number at the bottom, there's 3 ways of doing that. I was wondering why I was getting the wrong number. My apologies, 3. And here you could have 0, 1, and 2, and there are 6 different ways of distributing the energy in this fashion, with 1 at 0, 1 at 1, and 1 at 2. And the last way, of course, is to have 1 at 0, or sorry, all 3 of them with 1 unit of energy. And there's one way of doing that. So we have a total number of microstates for this system. It's just to add them up. 3 plus 6 plus 1. There are 10 ways of doing that. In order to, why is that 6? So the question from on the chat is, why is that equal to 6? Actually, I'm going to do it on the over here. It's going to make my life easier. Why is there 6 units of energy? And you can look at it in the distribution. If I have energy levels 0, 1, and 2, and we start putting molecules in there, we have molecules A, B, and C. It can go A, B, C, A, C, B, and then we put a different one down below. B, C, A, B, A, C, C, A, B, C, B, A. And there we have the 6 possible ways of distributing 3 particles, 3 units of energy. Does that make sense, Kyla? Good. We want to calculate the entropy. S is equal to KB natural log of the number of ways. And so you just literally need to look up Boltzmann's constant. Boltzmann's constant is 1.381 times 10 to the minus 23 joules per Kelvin times the natural log of 10. And when you do that, you get 3.180. Oops. Times 10 to the minus 23 joules per Kelvin. The entropy is a small number because we literally have only 3 particles and 3 energy. KB is always that number. It was derived by Maxwell-Boltzmann based on his work. So yes, it is always that number. It's just another constant like pi, okay, or Avogadro's number. It's a fixed value. This number with 3 particles, 3 units of energy, probably not meaningful, at least in a real-world context, but it is how we build up to determining the entropy in macroscopic particles. We're going to see tables where entropy is tabulated. And statistical mechanics goes from what we see are doing here to the values you see tabulated. That's not this course. That's an advanced graduate level or senior undergraduate course on Stat Mech, but it is possible to do that. And so this is what we have come to. Just in the interest of maintaining consistency between this and the other class, I'm not going to go into the next material because we didn't have time to go into it next day, but I will be starting that next day, so we're just going to finish a little bit early today. Unless you want me to continue, of course. You want me to continue, Ben? Really? Excellent. We're good here. All right. So you got a little bit of a break. Your term exam is on Wednesday, and of course, this isn't on the term exam. There is no, as just looking at the chat, there is no quiz on problem set 5. You will have the answers tomorrow. Will be posted tomorrow, and you will, that way you can help prepare study for the term exam on Wednesday. Are there any other questions? I can go back to that last example, but otherwise, have a great weekend, everybody, and we'll talk with you on Monday. See everybody Monday. And here's that last example for you, Kyla. Later, Emily.